Hi, Precalculus. We are working on the trigonometric functions on the unit circle. This should be exciting. So, our vocabulary requires us to kind of give some attention to this idea called the unit circle. So, the unit circle is pretty cool. What it is exactly what it sounds like. It's a circle with a radius of 1, usually placed on the XY axis, so we can discuss the idea of trigonometric functions, but not just from like 0 to 90 degrees, not just trapped in right angle triangles, but explored in a sense infinitely from 0 to whatever number of degrees you want to talk about. So how that works out is like this. Let's start off by putting a 30-degree angle right here. So if I put a 30-degree angle right inside of my unit circle, what I know is that I can make a triangle like this, right? This is a right triangle. And this right triangle would have a hypotenuse of 1 because it's a unit circle. And then here's where some of the cool things start to happen. I can kind of back solve and figure out what's going on for the rest of the circle, right? Or what's going on for the rest of the triangle. So somewhere in the back of your mind, you might remember this whole thing about 30, 60, 90 right triangles. And this came back as a result of you studying, this was, when you were studying geometry. So if we zoom a little closer into this thought, we remember that the side opposite the 30-degree angle had, let's say, a measure of length S. And therefore, we knew like the ratios of all the other sides. So the side opposite the right angle, which is the hypotenuse, was always double that other side, right? And then this side was always the smallest side. This is the side opposite the 60-degree angle times root 3. So if you hold on to that thought and we go back to our unit circle, what you're going to see is a relationship that we can kind of apply given the fact that we already know what the hypotenuse is. So if the hypotenuse is 1, the side opposite the 30-degree angle has to be half of that. So this length here is going to be 1/2. And if that's the case, we know that the side opposite the 60-degree angle, which would be up here, from here to here, this length would have to be 1/2 root 3, or root 3 over 2. Take a moment to think about that and try to remember how that goes, because this is really going to be important and impactful for what we're going to talk about now. So here's what I know. What I know is the x value of this point, stay with me, is going to be the square root of 3 over 2. And then the y value of this point, right, how far up we're going, is 1/2. Let's talk a little bit more about what's happening here. If I think about the cosine of this angle 30 degrees, remember we talked about SOHCAHTOA, right, as our mnemonic device to remember the ratios. Well, I know that the opposite over hypotenuse is just going to be 1/2. In fact, the cosine and sine, the sine of 30 degrees is going to be 1/2 over 1, right? And the cosine of 30 degrees is going to be square root of 3 over 2 over 1. Therefore, it's just going to be square root of 3 over 2. The beauty of the unit circle is that the hypotenuse is 1. Therefore, we know that the x term is always going to refer to the cosine, and the y term will always refer to the sine. So I'm going to write that down. So again, to reiterate, the sine of theta when we're dealing with a unit circle is always just going to be the y value of the point on which the angle intersects, the terminal ray of the angle intersects the unit circle, and then the x value of that point will be the cosine of the angle. And so that's pretty neat, right? Okay, I'm hoping you guys are as excited as I am. So we can go out to a 45-degree angle. And we know that a 45-degree angle, if you remember back in geometry, we had 45, 45 right triangles. I'm not going to draw the memory bubble for that one right now. I'm going to just hope you guys remember. So if the hypotenuse again is 1, and now I'm dealing with a 45-degree angle here, what I want you to know is that these two guys are equal in length. And we also knew that the length is going to be s times the square, well, no, it's just going to be the square root of 2 over 2. If you need me to bring some of these facts back to you, we can definitely sit down and break this whole circle down. But what I want you to see is that as we go around the circle, so we've got 45 degrees. Let me use another color. Okay, let me put this value in here. I'm so excited. I'm not writing all the information down. So the x and y value would be square root of 2 and square root of 2, right? Square root of 2 over 2 and square root of 2 over 2. So that says that the sine of 45 degrees is root 2 over 2. The cosine of 45 degrees is root 2 over 2 as well. And then we can move on. New color, new angle. Let's come up here to a 60-degree angle. 60 degrees, let's say that's 60. And I know some of my students are like super neat and they're like, we hate this. This is too messy. Be with me, my friends, just for a second. So what you see here, let me make that line a little bit better, is a 30, 60, 90 triangle again, right? So this time we still have the same 30, 60, 90 triangle, but this time we're referring to the 60-degree angle. So things switch. The width from here to here, the shortest side opposite the 30 degrees here, has to be 1/2. And therefore, this height, this y value, has to be the square root of 3 over 2. So what happens to this point here is that we have 1/2 as the x value. Cosine of 60 degrees is 1/2. And then the y value is going to be the square root of 3 over 2. And let's take this idea further. And I know we generally don't think about the sine and cosine of angles beyond like 89.999 degrees, right? Because we were keeping it in a right triangle situation. But what this gives us the power to do, thinking about it on a unit circle, is to say, okay, if we associate sine with y and cosine with x, then we can think about larger circles. Then we can continue to rotate around. So the next concept that I want to talk about is what happens here. What happens on this line here, which is what? This would be an angle that I can't really draw, a right triangle with two 90-degree angles. So now, considering this, I can say, well, what is the sine and cosine of 90 degrees? Well, it's just going to be the same thing as the coordinates of this particular point. What are the coordinates of this point? The coordinates of this point would be 0 for the x value and 1 for the y value. You guys with me? And therefore, I can say that the sine of 90 degrees is 1, whereas the cosine of 90 degrees is going to be 0. Continuing on, we can see that if we were to move over here, the next angle of concern that I'm going to talk about would be maybe a 120-degree angle. So we're all the way over here. If we're dealing with a 120-degree angle, now what we do once we have crossed this threshold is we're going to throw down perpendicular to the x-axis. Again, now what we're thinking about is the reference angle. So we're going to use the reference angle to talk about the situation that we have at hand. So this is a 60-degree reference angle. If this is 120, this bit is 60, and then you see what's going to happen. We're going to start to get the same values here, right? Well, not exactly the same, because now we're in the second quadrant. So the x value is not a positive 1/2 as it was over here when the reference angle was 60 degrees. It's going to be a negative 1/2, but the y value will still persist as square root of 3 over 2. So now this ordered pair is going to be 1/2 and negative 1/2 rather, the square root of 3 over 2. So what does this say? It says the sine of 120 degrees is a positive the square root of 3 over 2, and the cosine of 120 degrees is negative 1/2. And so we can continue along doing this, and I'm going to just fill this out for us real quick. Okay, so I just decided to go and grab this from elsewhere because I feel like this is a bit neater, and you can really pull this up anywhere. But if you look at it as we have here, we can, and again, I had to erase this, but I want you to remember that the sine of these angles, the sine of all of these angles is equal to the y value, whereas the cosine of any of these angles is equal to the x value on the unit circle. So you can see that we did these together, and then these guys are just a change in the quadrant. Therefore, all the x terms are going to be negative. And look what happens when we get down here. Both the x and y terms are negative, And then over here, the y term is negative, but the x term is positive. So this gives us some clue as to the sign of the sine and cosine values of each angle, and it gets deep. We could also say that the tangent of theta, from looking at this, will be y over x, right? Think about that. We know the tangent is opposite over adjacent, and that amounts to y over x. It really amounts to sine over cosine if you think about it as well. So I know we talked a lot about the unit circle. I know I spent a lot of the vocab time, but it's going to open up this idea that some functions have a cycle, have a period that keeps going back and forth, and that would be this kind of a circular function here. Sine, cosine, and tangent are all considered, and all of them are considered kind of circular functions, in that the value goes around and around and around and around. We're going to keep repeating the same values. So if I go from 0 to 360, past 360, I'm just using the reference angles again that are going to elucidate whatever the sine or cosine of that particular angle is. And then trigonometric functions, now we're looking at y equals the sine of theta or of x, y equals the cosine of theta and x, y is equal to the tangent of theta and x. Now we can look at this as a function where the domain would be any angle, right? The domain would refer to the angle values, and the trigonometric function refers to, just the process that we use to get those y values. So that is our vocabulary. Let's get started with some problems. So instead of using a handwritten one, we're going to use this picture, and I hope it's clear. It's not coming up super clear right now, but we're going to use the unit circle to find each of the values. What is the cosine of negative 180 degrees? So if we started here, negative 180 will bring us back here to 180, and we remember that the cosine of whatever angle we're dealing with is x value, and the sine of that angle is the y value. So let's hold on to that fact. And so when we go in negative 180, we can see that the x value is -1. Thus, the cosine of negative 180 is -1. Let's go ahead and figure out the secant. So we know that the secant is the secant of 90 degrees. We know that the secant is going to be the reciprocal of cosine. So if the cosine of theta is x, right, then the secant of theta is going to be 1 over x. Let me put a theta in there. All right, so let's go to 90 degrees. We're at 90 degrees. What is the cosine at 90 degrees? The cosine is 0. So if the cosine is 0, 1 over 0 is undefined. So the secant of 90 degrees is an undefined value. It's undefined. And we'll see that that comes up from time to time. So example 2 brings us to this example from the beginning of the text, where we're talking about in NFL history, at least at the time of the writing of this book, the longest punt was 98 yards. And so what we get in reading through this is that there is a formula, an equation that can give us the maximum height that is possible for a punt. And that formula is given as the initial velocity squared, that's what V naught is, times the sine, and look where the square is, of an angle. So when we write sine of an angle squared, we put the square sign on the sine, right next to sine, and not out here, because it looks like we'd be squaring the angle. Just a little bit of information. Okay, so V naught squared times sine squared over 2 times G, where G is the force of gravity. In this case, we're talking about meters per second squared. So I'm just going to plug in the information, and so we were given that 28 meters per second is a possible initial velocity. The sine, we're not quite sure what the angle is. We'll deal with that in just a second. Sine squared of theta, and then we've got 2 times G, which is going to be 2 times 9.8. Okay, so what we're doing here, let's continue reading through the problem. Suppose that the initial velocity is this. Describe the possible maximum height of the ball if the angle, the initial angle of kicking, that's what this theta is referring to, if the angle is somewhere between 0 and 90 degrees. I want you guys to think about this for a second. If the angle is between 0 and 90 degrees, and we scooch back up here and we think about the a unit circle and we think about the sine value, because we're taking the sine of whatever that angle is, and we're thinking about the sine values from 0 to 90 degrees, you can see that there is a consistent increase. The sine, again, is the y value. The y value goes from 0 to 1/2 to root 2 over 2 to root 3 over 2, all the way up to 1, and then it immediately precipitously falls back down to 0. Why am I pointing this out? Well, if we are trying to find the maximum height, we would need this value to be the maximum number. Yes, we're squaring it, but squared 0 is still 0, but a squared 1 is the highest value that we could have. Does that make sense? So the value that is going to give us the highest would be to put 90 degrees in here, because that is the highest sine value we could possibly get. And when we use our calculator and we do the calculations, we get that highest height that we can go is 40 meters. And so I guess it would be clear to say that we can go anywhere from 0 to 40 meters for the height. So here in example 3, we are going to use the unit circle to find the values of 6 trigonometric functions at 135 degrees. So the first thing we want to do is locate 135 degrees on the unit circle, which is right here. And so we need to just kind of riff on these points. So the sine of 135 degrees is going to be square root of 2 over 2, whereas the cosine is going to be negative the square root of 2 over 2. The tangent is going to be the ratio between sine over cosine, x over y. And so what we recognize here is that that's going to be same thing over kind of the same thing. It's going to be -1. And then over here, we're going to be using the reciprocals of cosecant. So the sine, the reciprocal of sine, which is cosecant. So technically we could write it as 2 over the square root of 2, because that would be the reciprocal of root 2 over 2. However, we know we like to rationalize the denominator in math, so we're going to multiply top and bottom by square root 2 in order to get 2 root 2 over 2, which is just square root 2. Are you with me how we did that? Does that make sense? We multiply top and bottom by the square root of 2, and therefore we got 2 factors of 2, like a factor of 2 of the top and bottom. That canceled out, we got root 2. Similarly, we would do the same thing with secant, but we're just going to get a negative root 2. Makes sense? We take the reciprocal, we process through, we get negative root 2. And finally, the reciprocal of -1 is -1, so we are done. So in example 4, we're asked to find the 6 trigonometric functions of theta, some angle, that we can create by drawing an angle in standard position, but having its terminal side rest at or cross 5, -12 on the xy plane. So let's go ahead and draw that into effect. So here's the angle that we're talking about. This is the theta that's going on here. And what I'm going to do is, you see we're outside of the unit circle, which is okay. We can still use the information we know to draw a picture and consider what's going on. So what we know is we've got this distance from here to here is 5. This guy here, the hypotenuse, is always going to be positive. If you think about the fact that it's, if we think about the idea that this is 5 squared and this is going to be 12 squared, and we would find the hypotenuse by using a squared plus b squared equals c squared. We take the square root of that positive value, that positive 25 plus 144, which is going to be positive, take the square root of, we get a positive value, we would end up with a positive 13 here. So this length is 13, this length is a -12, and so now we're going to use that information to find those 6 trig identities for this, or those 6 trigonometric value for this value theta. So the first thing we should do is find sine, cosine, and tangent. That's going to be the easiest thing. So if I'm standing at this angle and I want the sine is opposite over hypotenuse, I'm going to get sine is -12 over 13. Cosine is going to be adjacent over hypotenuse, so that's 5/13. Tangent is going to be opposite over adjacent, so that's going to be -12 over 5. Cosecant, secant, and cotangent, my friends, because they are just reciprocals, will be 13/12, the reciprocal of sine. This is going to be the reciprocal of cosine, so that's 13/5. And this guy is going to be the reciprocal of tangent, which is going to be negative 5 over 12. And that's it for section 5.3, the unit circle. I'd love to talk a little bit more about it because I kind of gave a quick overview, but there's lots to explore in the unit circle, and we're going to be doing that over time. But definitely let me know if you have any questions or concerns. Take care, sweeties. Bye-bye.